Hello everyone and welcome to lecture today. Today we'll be talking about how to extend the idea of definite integration to multivariable functions. So we're going to start with two variable functions and talk about double integration. So let's review a bit from single variable calculus. So the definite integral of a single variable function, you'll recall, is defined in the following manner. So if we have a function of one variable, maybe it looks like this, from say some point A to some point B, we define and we can kind of call the definite integral from A to B of that function the accumulation of the function. On the interval or over the interval from A to B. This is equivalent to thinking of it as the net area from A to B. So we have some function y equals f of x, and you'll remember from a Calculus 2 class that this is defined using what's called the Riemann sums. So we end up exactly mathematically defining this value by forming a partition of our region with n sub pieces under the function, which are actually rectangles, which we form by making the partition. This, say, is the first point in the partition, the second point in the partition, and so on and so forth, where there are n total points in the partition, and we approximate the accumulation by adding up the signed areas of rectangles under this function. So this means that we form our partition and then choose a sample point somewhere in each one of these subpartitions, and then look at the function value at each one of these sample points. This gives us a bunch of different rectangles, where the height of each one of these rectangles is the height of the function at the sample point. It could be positive or negative depending on whether the function is positive or negative. And we say that the approximation to the total accumulation of the function is the sum over all of these rectangles, the value of the function at the sample point, times the width of the rectangle. This is the so-called process of doing Riemann sums. And this summation approximates the total accumulation of the function over the interval from a to b. Let's include a couple more pieces of that partition here to kind of finish off this picture, this diagram. And if what are called the upper sums and the lower sums, the upper Riemann sums and the lower Riemann sums, if the limit exists for both of those and is identical as n goes to infinity, we say that the Riemann integral is the limit as n goes to infinity of this Riemann sum. Because it's like saying as the rectangles get smaller and smaller and smaller, this value is the true value of the accumulation of the function, or the net area under the function from a to b. We always have to be careful to think of this as a net area, not an area, because if the function is negative, right, it's not the actual area under the function. It's the total amount of area of the function above the x-axis minus the total amount of area of the function below the x-axis. So this is why we call it a net area and not just an area. Right? It's to deal with the fact that most functions are both positive and negative. So I know that visualizing this is sometimes a difficult task. So what I did was I created some Python code that goes through and actually visualizes this process of gradually increasing the number of rectangles and seeing this Riemann Sum Approximation in action for larger and larger numbers of rectangles. And in the title above, you can see the value of this approximation get better and better and better. The function I chose to demonstrate it on is the function sine of x over the interval from 0 to 2 pi. And we know that this function, the integral of this function from 0 to 2 pi will be 0. So the value of the approximation, you see, slowly but surely gets smaller and smaller and smaller. And the idea is that this Riemann sum in the limit as n goes to infinity is converging to 0, which is the value of this integral. For the sampling points in this animation, so the heights of each one of the rectangles, I chose just a random sampling point in each subinterval. So you see that the heights of the rectangles are just given by this randomly chosen sample point in each one of these subrectangles. And I also included just a visualization on a randomly chosen one of these rectangles, just to kind of visualize, right, that the number of rectangles is increasing here as we increase our value of n and decrease the width of each individual rectangle. So the idea is that we have to take this one-dimensional definition of the definite integral. Now I can box this in a bubble. This is kind of like a review from a single variable calculus course. And we want to take this idea now and directly extend it to the idea of the definite integral of a multivariable function. So let's see how to do this. And we're going to start this by defining the double integral. Which is the same thing as the definite integral in 2D, or the 2D definite integral. So in this class, we'll focus on double and triple integrals, but you can actually do the integral, the definite integral of a function of any number of variables, and the definition is very similar in any case. So we'll start by defining the double integral. And the notation for this is following. We say that the two integral signs stands for the double integral of a function of two variables, then dA. You also have to specify the region R that you're integrating over. So this is the notation for the double integral. And we'll kind of see why this notation is very important in a second. So this notation stands for the definite integral of a function of two variables over the region R. We can also call this, just like in 1D, the accumulation of the function f of xy over the region R. And we'll also see that this is a very nice interpretation as in a very, very similar manner to the 1D example. This is actually the net volume under the graph, or we'll say between the graph, of the function. So z equals f of xy in 3D. In much the same way that the single variable integral is a net area from a to b under, or we'll say between, the graph y equals f of x and the x-axis, which is y equals 0. The double integral of a multivariable function of two variables is the net volume under the graph z equals f of xy and the plane z equals 0. So this is one of the things that we'll see when we get into the applications of the definite integral. This is a very, very cool thing. Let's see how to define this. How do we define this? And the idea is just like we do in the single variable integral. I'll say a very similar process to the single variable integral. This is called the process of Riemann sums. And the idea is the following, right? We have that we're trying to define the accumulation of some function of two variables over some two-dimensional region R. So we have some two-dimensional region R here. where we'll say maybe the minimum value of the region R here is A, the maximum value of the region R here along the x-axis is B, but we also have the y-axis that we have to look at as well. So we'll say the minimum value of this region R is C, and the maximum value of this region R is D. So just like before, we have to partition our domain into a whole bunch of small pieces, very, very small pieces, and then sample the function at sample points inside each one of these pieces. So the way that we do that can be very, very varied. The easiest way of doing it, just like in the 1D case, the easiest way of choosing the sample for this Riemann sum, and here we call the sample point CK, but I think what I might do is relabel this to XK star to denote the sample point, just because I think this is a better notation to denote that we're sampling points of X, so points from the domain. This is going to be, this point right here is X1 star, this point right here is X2 star, X3 star, and so on and so forth. So remember that the simplest type of Riemann sum is when we use a uniform partition. And that's when delta xk is just equal to the length of the interval divided by the total number of subdivisions in the interval. So the same thing is true for the multivariable case as well. But we'll just be as general as possible. So let's say we do a partition along x, and then we also partition along y. So what this looks like is that we end up cutting up our domain R into a whole bunch of pieces along x here. And similarly, we cut up the domain R into a whole bunch of pieces along y. Let's include a couple more pieces in the partition to really show that. We can really do this and make really a very fine partition. And really, we can get as accurate as we want in terms of cutting up our region into a whole bunch of very small pieces. So the idea here is that we have for a function of two variables, we have two separate variables that we have to partition for any domain that we're trying to integrate over. This is the first step in double integration, is forming this partition. And then once you form this partition, you have a whole bunch of different subrectangles. And if we say zoom in to one of these subrectangles, let's say we zoom in here to the kth subrectangle. This is going to be a rectangle that has a width of delta xk, which is the width of the rectangle in the partition, a height or a depth of delta yk, which is the height of the kth subrectangle in the partition. And I'll actually probably, instead of k, I'm going to use I and j. So specifically, we'll say we have, for each one of the partitions along the x-axis, we have that I, right, goes from 1 to n, where I is the point, the x point in the partition. So this corresponds to I equals 1, I equals 2, I equals 3, and so on and so forth. And same thing with the y-axis as well. We have a whole bunch of points, let's say we have the same number of partitions along y, so from 1 to n. You can do a different number of partitions along the y-axis, that's perfectly fine, but it makes it easier in terms of computation if we just use the same number of subrectangles along both x and both y. But so the idea is that each one of these subrectangles has a width delta xi and a height delta yj, and then we also have to choose a sample point. We'll call it xi star yj star in each one of these subrectangles. So each one of these subrectangles has some sample point chosen in it, in which we evaluate the value of the function at that sample point. So just like for a function of one variable, it's the same process really, just a little bit more complicated because the domains can be more complicated in 2D. The domains that we're integrating over. But we still, the Riemann sum procedure still consists of two steps. The first step, two main steps. The first step being that you have to choose a partition. And step 2 is that we have to choose a sample point. And then doing that, the Riemann sum becomes the following. It's Sn is going to be the sum over all of these rectangles, which is actually a double summation. It's a sum from I equals 1 to n of the sum from j equals 1 to n of the value of the function at the sample point times delta aij, where delta aij is the area of the sample point or the sample rectangle, the partition rectangle, I should say, of width delta xi and height delta yj. So this is the correct formula for a Riemann sum for a function of two variables, and it's directly, I shouldn't say directly the same because it's a little bit more complicated, but it's very, very similar to the Riemann sum formula in 2D for a single variable function. So for a function of one variable. Now it's really important for me to emphasize here that this is a double summation, right? Where in order to get this Riemann sum, you have to go through and you have to sum over all values of I and j from 1 to n. This is x 1 star, f at x 1 star, y 1 star times delta a 1 1 plus f at x 1 star, y 2 star, delta a 1 2, and so on and so forth, plus f at x 2 star, y1 star, delta a1, 1, and so on and so forth. We have to do this procedure all the way until we get up to the function at xn star, yn star, delta a, and n. So in 1D, right, we only have a single sum in our Riemann sum. This Riemann sum has n terms in the sum. But in 2D, for a double integral, we actually have a much larger sum because we have n squared rectangles. If there are n rectangles or n terms in the partition along x, and there are n rectangles in the partition along y, then that means that this summation is going to have n squared terms in it, because you're going to have that many rectangles that you have to sum over in your Riemann sum. So it's a much larger sum than before. But the main idea here is that just like before, you can consider what are called the upper Riemann sums and the lower Riemann sums. And in the case of 1D, for a 1D integral, right, we say that if this limit exists, the limit as our partition gets finer and finer and finer exists, and the limit as n goes to infinity of the lower Riemann sums is equal to the limit as n goes to infinity of the upper Riemann sums, then we say that f is Riemann integrable. Well, we have for a double integral exactly what the Riemann sums are, and we have the exact same statement. Right? We say that if the limit as our partition in 2D of the Riemann sum formula, the limit of Sn, exists, and the limit of the upper sums is equal to the limit of the lower sums, then f is Riemann integrable. On the domain R. And specifically, we can evaluate the Riemann integral, or the Riemann integral, by taking that limit. So if we have a nice expression for our Riemann sum for a function of two variables, the double integral of that function is just the limit of this Riemann sum as the partition gets finer and finer and finer, or smaller and smaller and smaller. And so to illustrate this point, I decided to show how the Riemann sums work for a function that we're very familiar with, the function x times y times e to the negative x squared plus y squared. And this is a symmetric function. And what I'm showing right now is the Riemann sum approximation for the double integral of this function over an elliptical domain that's shifted to the right by a little bit. The function is still symmetric over this region, so we expect the double integral to converge to 0 because the total accumulation of the function in this region is 0. And this is exactly what we see. So this is very, very neat. Not only that, but if we consider the three-dimensional graph, the graph of this function of two variables, the double integral that we're getting, this accumulation value that we're getting, is actually the same thing as the net volume bounded by the graph of this function of two variables. And you can very clearly see in this animation we're showing this, that what we're doing when we're adding up our Riemann sums is adding up the volume of approximating subrectangular prisms that are above and below the xy plane. So this value that we're calculating is the net volume bounded by the graph of the function of two variables. So this is a very, very neat thing and is going to be very useful to us when we go to calculate volumes. Now the idea is that we're going to see there are much easier methods for evaluating the double integral than doing Riemann sums. Very, very often when you want to take the double integral of a function, you actually don't even consider the Riemann sums because it's too hard to deal with finding that Sn. Simplifying that into a closed form expression is often very hard, if not impossible, to do. Which is the same situation as in 1D for single variable functions. Typically in a Calculus 2 course, when you go over the integral, you see the definition of the Riemann integral, and then very quickly get into alternative means like the fundamental theorem of calculus and other methods of evaluating the integral, because it's not computationally feasible to do Riemann sums for even not even complicated functions, but for relatively basic functions, it gets almost impossible to do. So there are much easier methods at our disposal. But the idea here is that it's very good to see this Riemann sum formula, and it also, it allows us to actually get certain results for certain and see certain results almost immediately if we know how to use it. So we will be coming back to it when we go into certain applications. It's also very useful for approximations. Sometimes you have a function that just, no matter how good you are with taking the integral, it's just too difficult or maybe even not possible to evaluate a closed form expression for the integral. So you have to rely on this Riemann sum formula if you want to do this and actually evaluate, or I shouldn't say evaluate, but approximate the integral. So the first function, and probably the simplest function to figure out the integral of, is going to be an important one for us because it's going to be a direct method that we use to calculate the area. So what I'll start with my first example is try to figure out what is the double integral of the constant function 1 over any region R. Or the double integral of the function f of xy over R when f of xy is just equal to the constant function 1. So by our definition of Riemann sums, this is the limit as n goes to infinity of Sn which is the limit as n goes to infinity of the double summation over I and j of the function, which is just 1, times delta aij. So what is this limit going to go to? Well, if we look at what Sn is, which is this double summation, right, the sum of all of the rectangles over the sum of all the rectangles in our partition, this double summation is just an approximation to the total area of the region R. So in the limit, as these rectangles get smaller and smaller and smaller, this should give us the total area of the region R. And this is exactly what we get when we take the double integral over any region. It gives you the total area of that region. This is the double integral of the function 1, the constant function 1. So in general, if you're asking to solve for the area of a specific region, you can do that by just taking the double integral of the constant function 1. So we'll see how to use this formula in detail in the coming lectures. But what I wanted to do was just show that this is definitely giving us the correct result, even using this Riemann Sum Approximation. So let's just consider a relatively simple example, say a circle of radius 2. And we'll actually prove the formula for area that we get for the circle a little bit later on when we get to polar coordinates. However, it's possible to do in Cartesian coordinates as well using the double integral. But this formula is that the area of such a circle is going to be pi times the radius squared. This is the formula that we'll end up getting, and should be hopefully familiar to you from an earlier geometry class that you've seen. So the area of such a circle is going to be pi times 2 squared, or 4 times pi, which is approximately 12.56637.1. And this continues on infinitely. However, what this means then is that for large values of n, the Riemann sum approximation should be approximately equal to this 4 times pi. And sure enough, if we jump to visualization of this Riemann sum approximation, this is exactly what we're seeing. And I will always be surprised at how long it actually does take to converge, and how many rectangles you need to get an accurate approximation, even when you're going to, say, just the hundreds place in the decimal. However, the point is that in the limit, as n goes to infinity, we do get convergence. And there are ways of speeding up this convergence by considering different, more advanced types of finding your Riemann sum approximation formula. If we take into account the boundaries of the domain and change the shape of the rectangles, we can very often get better approximating formulas, which better utilize the domain in question. However, this is a very, very neat result, and it's neat to see this in practice, even with Cartesian coordinates and rectangles. And you can see, for instance, that we have to go up around 80,000 rectangles to just get into the 100th decimal place of accuracy to the actual value. So this is a very interesting demonstration. More generally, if you take the integral of a positive function, and to visualize this, we're going to use the graph of the function in 3D. So let's say we have some region R, and a positive function defined in that region. So we know that this is going to be some surface that is going up and down on the region. So this is our region R. And this is our surface, z equals f of xy. So it's the graph of the function f of xy. When we partition our region R into a whole bunch of small pieces along the x-axis and then along the y-axis, in each one of these pieces we have a sample point and at that sample point we take the value of the function. And so what we get is another rectangle, the height of which, a rectangular prism I should say, the height of which is given by the value of the function at that point. And the double integral is the sum of the function times the height of this rectangular prism times the area of the base. Right, so the Riemann sum is the summation over all of the rectangles in this partition of the value of the function at the sample point, which is the height of this rectangular prism, multiplied by the area of the base. So if the function is a positive function, then the double integral over the region R of that function is the limit as n goes to infinity of this Riemann sum. This Riemann sum is an approximation to the volume under the function, or the graph of the function f over the region R. So in the limit as n goes to infinity, this Riemann sum goes to the exact value of the volume under the graph z equals f of xy over R. So this is how we can calculate. It gives us a method of calculating volumes as well. Now I want to emphasize here that this volume, this is the volume only when the function is positive on a given region. If the function is negative for certain points, we've seen before that it's really the value that we're getting from the integral, the double integral, is the accumulation of the function, or the net volume. Right? So for a general function, this is not necessarily positive. The double integral over the region R of the function is the net volume, or the volume of the function over the xy plane, under the graph of the function, minus the volume under the xy plane. Now, to see an example of this, let's try and use this, just the Riemann Sum Approximation, to go through and evaluate an approximation to the volume of the hemisphere, we'll say of radius 2. So the hemisphere of radius 2 is the equation given by z is positive and x squared plus y squared plus z squared is equal to 4. Which means that z is equal to the square root of 4 minus x squared minus y squared. And the domain here of integration, R, is then going to be the circle of radius 2. This is when z equals 0. And the volume is going to be equal, or should be exactly equal to, the double integral over R of this function and we have a nice formula for this that we should know from maybe a previous geometry course or previous calculus course, from the volume of the sphere, which is 4/3 times pi times rho cubed. Then we have to divide this by 2 because we're just considering the hemisphere. Now, a little bit later on, when we get to spherical coordinates, we will actually derive this exact formula, and it's relatively straightforward to go through and do. However, for right now, what I want to just do, right, is take this value that we get, which is 2/3 for our sphere of radius 2, 2/3 times 2 cubed, or 16/3 pi. And I want to show that this value is well approximated by the Riemann sum formula, which verifies, was a good example showing the previous statement that we were talking about. And so here we see a 3D view of the graph of this function, as well as the Riemann sum approximations for the double integral of this function, square root of 4 minus x squared minus y squared. And you see very clearly that as the number of rectangles in our approximation increase, this value is getting closer and closer and closer to the actual value of the double integral, which is the volume of the region under the graph of this function, which is exactly the hemisphere of radius 2. So this is very neat.